Hello everyone. We shall discuss about file systems in Linux operating system now. Now, as we all already know, Linux basically retains the standard file system model of the UNIX operating system. Okay, it follows the UNIX semantics in implementing the file system. And before going into the details of the file system of Linux, let's try to recall what is the meaning of a file system. So file system is a logical collection of files on a separate partition in the disk or in the it can be in a separate partition on the disk, or it can occupy the entire disk. Okay, for example, one partition on your hard drive may contain /home file system, another partition on your hard drive may contain /user file system, etc. So either you may have your file system in one of the partitions on the disk, or your file system may occupy the entire disk. So both cases are possible. And in Linux, anything capable of handling the input or output of a stream of data will be considered as a file. Okay, so it means that your DVD-ROM can be a file, your USB drive can be a file, your network connections can be a file, or your interprocess communication channels also will look like files to the user. Okay, in Unix and Linux, anything which is capable of handling the input or output of a stream of data will be considered as a file. Okay, so the Linux kernel will handle all these types of files by hiding the implementation details of any single file type by using one particular type of software called as the layer of software called as the virtual file system. Okay, so everything is going to look like a file to the user, irrespective of including your device drivers or CD-ROM or a DVD. So it is going to look like a file to the user, but then the implementation details are hidden from the user by using this concept of virtual file system. So in this topic of file systems in the Linux operating system, let's learn about how the virtual file system is implemented in Linux, and then we'll learn about the standard Linux file system, which is nothing but the second extended file system. And then we'll also learn about how journaling and what is the meaning of journaling in Linux operating system. So let's get into the details. And before getting into the details, just let's go through some real-time facts. So I told you that Linux file system is based on the semantics of Unix file system, and Unix makes use of a hierarchical file system structure. Okay, the root will be at the base of the file system structure, and the root directory will be represented by the /. And this root directory will contain all the other files and directories, and every file or every directory will be having a unique identifier, which is nothing but it is called as inode in Unix and Linux. So we have many directories which are commonly used, for example, which are famous. For example, / is your root directory, which will be at the top level of your directory structure. You have /bin, where the executable files are stored. You have /home, which will be your home directory for user accounts and as well as for other accounts. You have /mount, which is used for mounting other temporary file systems, etc. Okay, so next is about the virtual file system in the Linux operating system. The Linux virtual file system is basically designed around object-oriented principles. Okay, so we know that when it is following object-oriented principles, then it means we should be having objects, and we should have defined the operations to be performed on those objects. Okay, so here also the Linux virtual file system basically has two components. First thing is it consists of definitions which will specify the different types of file system objects, and the second is a layer of software which will define the operations which can be manipulated on the objects. So virtual file system consists of file system objects as well as the operations which can be performed on the objects. So when I say objects in the virtual file system of Linux, there are four main object types. Okay, namely the inode object, which is used to represent an individual file, a D entry object which represents an individual directory entry, a file object which represents an open file, and a super block object which represents an entire file system. So first is about your first let's learn about your file object. So before that, I told you that there are four different types of object types, namely inode object, file object, super block, and D entry object. But then, in case if the virtual file system wants to perform any operation on this object type, it just will every object of this types will contain a pointer to the function table. Okay. So we maintain something called as function table, and that function table will contain the actual addresses of all the functions which will perform the operations for these objects. Objects means they can be manipulated by using the operations which can be performed on the object. All these operations or the addresses of these functions which will implement those operations will be present in a function table, and every object will maintain a pointer which points to the function table. For example, if you take your file object, the list of operations which can be performed on your file object can be, you can have the open operation, read operation, write operation, memory map operation. So for this you may have functions defined accordingly with appropriate return types, and they may all be stored in the function table. And complete the definition of the file object is actually present in real implementation in a structure called as file underscore operations, and that is actually present in a file called as fs.h, which is defined inside usr/include/linux directory. That is, it is present inside the Linux directory in a file called as fs.h. Okay, so whenever the virtual file system layer or the virtual file system software wants to perform an operation on one of the file system objects, it will just call the appropriate function from that object's function table. Okay, it need not know what type of object it is dealing with. As I told you already, everything will look like, everything will be considered as an object. So it might be every type of anything which is capable of handling the input or output of a stream of data will be considered as a file, and so it's going to be represented as an object. So the virtual file system layer need not know what kind of object it is dealing with, but it just will be calling the appropriate function from that object's function table. Okay. So next is about the different types of object types. So first is the inode object. So what is the use of this inode object? With the help of the inode object and the file object, the processors will be able to access the files. So this inode object is going to contain pointers which actually point to the disk blocks which stores the actual contents of the file. Inode object contains pointers pointing to disk blocks storing the actual contents of the file. Apart from that, all the directory operations, like you can create or delete, can do such type of operations on directories, right? So all these directory operations are also defined in the inode object. Okay, previously I told you that there are two types of objects to deal with files. Inode object will contain pointers which points to the actual disk blocks containing the data, and file objects will store information about the open files. So but then in directory also we contain files, but we don't have to open the concerned files of the directory. So information about the directory operations will be stored in the inode object, and that's why it's not stored in the file object. Next is the file object and the superblock object. So file object acts like a point of access to all the data which is there in an open file. Okay, let's say when a file is opened by a particular process P1. So this file object will serve as a pointer for accessing that particular data in the open file. So later on, if any other process wants to access that open file, it may access it through this file object. So this file object also monitors the point where the process is currently reading the data or writing the data. It keeps track of the sequential file input output operations. And next object is your superblock object. In your superblock object, it is nothing but it represents your file system, and it represents all the set of files present within your file system. And for every device which is mounted like as a file system, a single superblock object will be maintained, and for every file system which is connected through the network also, a separate single superblock object will be maintained. And generally this superblock object points to inodes, and so by accessing the superblock object, the kernel will be able to access the inodes of the file. The next one is your directory entry object, which is called as dentry object. So this directory entry object is nothing but it contains the information about the names of the directories in a file's path name, or it may also contain the names of the actual files. Say for example, if your file path name looks like this, /usr/include/stdio.h. This is example path name for a file. So here your dentry object will contain each entry. So each of those entries in the dentry object will be slash will be one entry, usr will be another entry, because slash represents your home directory. USR represents another directory, then include represents another directory, and stdio.h is another file present within these directories. So for each of these directories and files, entries will be created and it will be represented by a separate dentry object. Okay. So next is the second extended file system of the Linux operating system. Now, when Linux was initially designed, it was originally programmed for the Minix file system. Okay, Minix file system for exchanging data with the Minix platform. If you're wondering about what is this Minix platform, Minix was actually a platform. It was actually an OS which is designed for academic purposes by Andrew Tannenbaum in 1987. But then the modification to the existing coding of Minix platform was very restricted. And hope you would remember Andrew Tannenbaum, who has written many books on operating systems as well as in networking. Okay, so initially when Linux was developed, it was developed for this Minix platform only, but then later, and then it was programmed with this Minix compatible file system. But then later they replaced this Minix file system with a new type of file system designed exclusively for Linux, and that was called as the extended file system. That's why it's called in short as EXTFS, which stands for extended file system. And then later they redesigned this extended file system just because it was an extension of this EXTFS. It was called a second extended file system. We write it as EXT2FS. So some improvements in performance and scalability was obtained in this second extended file system. And nowadays we have this Linux supports many other different types of file systems like third extended file system, fourth extended file system, XFS file system, etc. And in the second extended file system, directory files are also stored like normal files, though directories don't store contents of the file. They store information about the files, but still they are also stored on the disk just like normal files. And for each directory file, there will be a block. Each block which is allocated for the directory file will contain a linked list of entries. Okay, and each entry will contain the information like what is the length of the entry, what is the name of the file, and what is the inode number of the inode to which that entry refers. Okay, that a directory may contain several files or subdirectories. So it will contain each entry of that directory file will contain each entry for the block allocated to the directory file will contain the inode number of each file or subdirectory which it is referring to. That is maintained with the help of a linked list. So as an example, you can see that as a real-time example, if you want to know what is the type of file system which is currently present in your Linux system, we can make use of the df command. Df stands for disk file system. Now you can use the -t option along with the df command to know the type of file systems available in your Linux system. Here you can see a snapshot of the df command with -t option, and it shows all the list of file systems which is being currently in use in the Linux operating system. So the next is the allocation policy for this second extended file system usually comes in two parts. Okay, so what happens is that generally the file system will be partitioned into multiple block groups. In the second extended file system allocation policy, the file system is partitioned into multiple block groups. Each block group corresponds to a particular single cylinder of a physical disk. And this each block and allocation in the second extended file system may involve, it may have to allocate space for files, it may have to allocate space for the inodes of the files and directories. And that is, you will be maintaining inodes for files, you will also be maintaining inodes for the directories. So space has to be allocated for inodes, and then you will have to, the file system has to allocate space for the directories. So in case allocation has to be done for a particular file, then how it will be done is the second extended file system will select, has to first select which block group the file has to be allocated. So if it is a data block, then it will try to allocate that file in the same block group where the files inode has been already allocated. Okay, in case if it has to allocate space for an inode, then the file allocation policy has to select the block group in which the file's parent directory resides, and this inode will be allocated the same location, same block group where the file's parent directory resides. Or in case if the allocation has to be done for a directory file, then it can be allocated to any of the available block groups. Usually it's not kept together, so it may be allocated in any of the available block groups. So this is how space is being allocated in the second extended file system in Linux allocation policy. Now this diagram shows a snapshot of the second extended file system block allocation policy. So within a block group, I told you that memory will be, that is the space will be allocated, space will be allocated in terms of multiple block groups. So within a block group, the second extended file system tries to keep allocations physically contiguous as far as possible. Why it tries to keep it physically contiguous is in order to reduce fragmentation. So it maintains a bit map of all the free blocks in a block group. Okay, so whenever allocating the first blocks for a new file, it starts searching for a free block from the beginning of the block group. Whenever free block has to be allocated, it starts searching from the free block of a block group. So here you can see that the shaded ones represent the blocks in use. The dot means that this block has been selected by the allocator. The light lines represent the bit boundaries and the dark lines represent the byte boundaries. And these arrows indicates the search inside the bitmap vector. And whenever you have blocks like this, it means that the block is free. Okay, so whenever first block free blocks has to be allocated for a new file, it starts searching for a free block from the beginning of the block group. And when extending a file, whenever a file has to be extended, it continues the search from the block which is most recently allocated to the file. So from this diagram, you can understand that in the second extended file system, the file system usually maintains a bitmap of all the free blocks in the block group. Each row represents a sequence of set and unset bits in an allocation. So that means if the bitmap is set, it means it is used, and if the bitmap is not set, it means it is free block on the disk. So see here you have two cases, first case and the second case. So in the first case, what happens is we can find free blocks near the start of the search. The search starts from here. You can find free blocks here and here within the byte boundary. So from the start of the search, you can find free blocks. So here the file system will try to allocate them even though they are fragmented, because they all can be read without any disk seek operations. Even if they are present within the same byte, so it's better than allocating isolated blocks. Okay, so even though it may create fragmentation, whenever it finds a free block near to the search, then it will try to allocate it. In the second case, consider the second case. So in the second case, we search for the entire free byte in the bitmap. Okay, here we are not able to find any free block close by. Okay, in this entire byte vector, we are not able to find any free block. So, so we have to search the entire bitmap for the free bytes. So here, let's say it tries to find a free block here. Okay, here if it tries, it gets across a free block. What happens is it will do something called as backward extension. So what is backward extension is that, so whenever it gets across a free block, it goes backwards until it gets the next allocated disk block. Okay, so here it finds a free block, it moves backwards one block by another until it gets the allocated disk block. Okay, so here if it finds a free block here, it performs backward extension. It moves across the block one by one until it finds an allocated disk block. So here it is able to find another free disk block, and then it allocates it, and then it finds across this one, this one, this one. It allocates all of them until it reaches the allocated disk block here. Now this is called as backward extension policy. Okay, why this backward extension is being done is, if this search is not done, means that there is a possibility of hole being created here, and that will result in fragmentation. So in order to avoid that, you can see here that it finds the disk block here, but then it performs backward search, backward extension, and moves up to the next allocated disk block, and then backs up all of them, and then it moves forward until it allocates, until it performs a default allocation of 8 disk blocks. Now this is called as, it by default it allocates 8 disk blocks, whether the file requires it or not. By default it will allocate 8 disk blocks. Why it will allocate 8 disk blocks? It will allocate the 8 disk blocks, and that is called as pre-allocation of disk blocks. Why it will allocate 8 disk blocks is in order to reduce the it reduces the CPU cost of disk allocation by allocating multiple blocks simultaneously. By doing this pre-allocation of disk blocks, it aims to reduce the CPU cost of disk allocation. Okay, one is, so from this you can understand that there are two block allocation policies which is followed. One is backward extension and finding out the free disk blocks in order to avoid fragmentation and the creation of holes. Okay, and the second one is pre-allocation of disk blocks. By default 8 disk blocks are allocated, and so it aims to reduce the CPU cost of disk allocation by allocating multiple blocks simultaneously. So that is being illustrated here. As I told you, it aims to reduce fragmentation, and as well as it also aims to reduce the CPU cost of disk allocation by allocating multiple blocks. By default, it allocates space for 8 disk blocks simultaneously. And similarly, it also provides for backward extension. Whenever a free byte is spawned in the bitmap, it aims to do, the search is extended backwards until an allocated block is encountered. Okay, search is extended backwards. That's why it's called backward extension. And it prevents the creation of a hole between the most recently allocated block and the previously allocated block. And by that, it is helpful for preventing fragmentation. The next concept is called as journaling, which is a popular feature in Linux file systems, where whenever any modifications are done to the file system, it will be sequentially written to a journal. Okay, here we have a terminology called transaction. Transaction is nothing but a collection of operations which perform a task is called as a transaction. So whenever a transaction happens, it will be periodically written to the journal. And whenever a transaction is written to the journal, it will be considered as committed. Okay, once the transaction is committed in the journal, then the system call will return. So let's say you are using the write system call to perform the transaction. That system call will be returned to the user process, and the user process is said to continue. So let's say in such a situation, if any in such a situation, the journaling file system will always maintain a pointer, okay, to indicate which actions are completed and which actions are still incomplete. Only when the entire, all the operations concerned with the transaction is completed, then the transaction will be removed from the journal. Okay, when all the operations concerned with the transaction is completed, and when an entire committed transaction is completed, it will be removed from the journal. Now the problem here is, let's say there is a system crash. Okay, some transactions would have been written in the journal, some transactions would remain in the journal, they would have been committed by the operating system, but the system call would have not returned back to the user process. So even though the transactions are committed by the OS, they are not completed for the file system. As far as the file system is concerned, they are not completed because system call is not returned to the user process, and the user process has not started its continuation. So in that case, what has to happen is all those uncommitted transactions which are not completed for the file system has to be completed after the system recovers. How it will know from which point it has to restart is, already a pointer is maintained inside the journal file system, right? So the transactions will be executed from the point using the pointer. Okay, using the current position of the pointer, we'll be able to know until which position the work is completed, and from that position the remaining work can be continued to be completed. So this concept of journaling file system ensures that all the file system structures remain consistent even in case of a unexpected event like a system crash. So this journal is usually maintained like a circular buffer, and it might be residing in a separate section of the file system, or it may be even in a disk spindle. Even it may be residing in the separate disk spindle. So that is all about the different concepts of the file system in the Linux operating system. Thank you.